and speaking something related to speech, whatever we are working and whatever we did earlier. And I'll make this presentation a bit simple. I'm assuming like you have some bit of knowledge about speech and all, because I saw like so many interesting lectures was there like before me and after me also, like there are so much exciting sessions are there, so you can learn so many things from this whole summer school actually. Now, so what I am planning is now today is to give some brief overview of speech foundation models. I think nowadays you all of you know about this GPT, then BERT, then Chat GPT. All those terms you heard about that. Okay, so these are called actually foundation models. So those models are related to your NLP, like text related data. But for speech also we have some this kind of models which you can use for different tasks actually. Okay, so we'll discuss about that on that direction. Okay, so I'll share my screen, and I'll stop my video and
yes, sir.
share.
You can stop.
Okay. So how to share the screen? Directly I can share my screen.
No, sir. You have to first open the PPT, then you can select that particular window. So nowadays,
Yeah.
full screen option is not coming in Zoom. Why, I don't know.
Okay. Just give me one.
Yes. No.
So I want to share my screen, but I am having only this share button is there, no? So that I need to press. So if I do, I am having.
Then share that window you have to select. Then after share option, you have to select that particular window.
Yeah, so but I am getting like photos, then iCloud drives, and then website URL and bookmark. I am not having that other things actually, screen share and all.
Then you have to screen sharing option I have already given.
Can you check once? It is.
Yeah. So first is you have to, that basic option is there. Now whenever you're going to share the screen, and the right hand side option is there, you can share sound if you want to share the sound. Then
Yes.
You have to select the particular window. Suppose in one window PPT is there, select that window.
Can you show me? Can you just share and show me once?
Yeah. So here I'm sharing my screen. Okay. So here, it is visible.
Yeah, it's visible.
Okay. So like this only, you have to share that particular. First, you have to select that particular window. Say that open the PPT, then share option. Then in basic, you have to select that particular window which you want to share.
Basic means in Zoom tool only.
Yes,
right?
Zoom, yeah. Go to share screen, click there.
There are 4 options only, photos, and then I'll try with my different PC once. Just 1 second.
Sir, are you on different OS? I mean, it's in here.
Yeah, I am with this one. No, I'm with this. I am using iPad.
You are using iPad, sir. I think you should use the Zoom's browser. You should use Zoom from browser because it's
from
some new.
browser. Right?
You just go out of the screen and again re-enter.
Oh,
Okay,
great,
so
great. Fine, fine,
we
fine.
enter with the
Thank
Zoom
you.
that browser try to.
Okay, okay. Okay,
Zoom has
okay, okay.
changed something, so that's why it is not updated on different platforms, I think.
Oh, okay, okay. Thank you, thank you. I'll just let me just give me 2 minutes. Just 1 second.
Deepsankar,
Yes, sir.
okay, as I told you, I have to leave, okay, from 12:15 around to 1:30. So you have to
Yes,
take care.
sir.
I have already
Yes, sir.
make you host, co-host, okay? If any problem is there during the sharing, you can handle, okay? Because you have all the options are there in cost also. Recording I am
Okay,
doing,
okay.
don't worry for the recording, okay? But rest
Okay,
of the things you can handle from there. If
okay,
if
sir.
sir
Okay.
is not able to share in case, then you can share in your system. I think sir can. If any problem, you can share in your system that PPT like yeah. Now just try sir.
Am I audible, sir?
Yes, yes, you are audible,
Yes,
sir. So
yes,
share
sir.
this.
Yes.
Okay, 1 second. I am pressing that share screen, but still let me open from different PC. Just
Share screen option.
no, actually when I am pressing the share screen, no, it's not
Uh,
actually happening. Nothing actually. Just 1 second.
is it then?
So,
Again, try to give because I have already given the option.
host disable screen sharing actually.
You can just do it now because I have already given the option. Yes, yes, it's coming.
Coming, no? So
Yes,
I'm doing okay. I'll do from this one, a
yes.
different this one
Ah,
PC.
when the PPT down.
Okay, uh, fine, fine, fine.
Sir, in between the session, I will not be available for, I think, for the 15 to 20 minutes. You can just handle. Okay, I have already made you the post. Okay,
Fine, fine. Okay, sir. Okay, okay.
and if something
Thank
is
you,
there,
sir.
take care.
So,
Then open the PPT.
so it is visible, no? Now there is no problem.
Visible, your screen is visible.
Okay, fine. I don't use actually Zoom, so I don't know this problem.
No, sir.
So,
It is because of some recent update. If
oh,
you the Zoom's app isn't working, so if you are accessing with the browser, it will be fine.
Yes, sir, your screen is coming. Just make it the full screen, slide mode, presentation mode.
But you are not audible. You have muted yourself, sir.
Sishir sir, you are not audible. This is a unmute yourself. You are not audible.
Yes,
Sir,
I
sir
think
has
he said 1 minute he's coming back.
Okay, okay.
he's written something in the chat.
Thank you, Bala.
Hello. Am I audible now?
Yes, yes, yes.
Okay, sir.
Ye-
Okay,
yes,
sorry
sir.
for the inconvenience. Okay. Okay. So, as I discussed, I'll talk about different speech foundation models and what foundation models is. So that I'll discuss. So this is like whatever flow is for my talk. Like we'll discuss very brief, maybe five minutes of about like understanding speech signal. What is actually handcrafted features? Now, what is the idea of pre-training? What is representation we get from training that foundation model? And then to train the foundation model, we need something called self-supervised learning, and different state-of-the-art SSL models, self-supervised based foundation models are there. Web2Vec by Facebook and Hubert from Google and WebLM from Microsoft. So there are other models are also there, but we can see like these models are there. Okay, so just ignore this coding session. This I took from other presentation. So now if you hear a speech signal, for example, whatever I am speaking, so you can what information you can get. So you can get different information. For example, one information is message. Okay, so that means what I am speaking. That is one information. Then second information maybe gender. Okay, so a male or female. Okay, that information you can get from the signal. Okay, then speaker information. Okay, so speaker information means whether I am Sishir, so that information also you can have. Okay, if you listen my speech earlier. Then emotion, like currently I am in a neutral emotion, for example, then that kind of emotion you will get some pathological problem. So different lots of information is present in that particular speech signal. Okay, now how to represent those information? Okay, so that you can use those information or use that representation for different tasks. Those tasks may be your this task, for example, speech recognition or synthesis you want to do. Okay, or maybe spoken language understanding. Okay, whatever I am speaking, what message I am having. For example, I am just give an example. I am talking about speech foundation model. So if you give this whole speech of me, maybe 2-3 minutes speech to one model, so it will say like he is talking about foundation model. Okay, so that is language understanding. Now speaker and language identification. So currently I'm speaking in English. Okay, so that information is there. Then speaker derivation. Okay, for example, me and Setas are speaking something, and then at what time I am speaking and what time Sar is speaking. So that is speaker derivation. Okay, in meeting application, those things are required. Then emotion recognition. Okay, pathological speech enhancement. So all those different tasks are there. Okay. Now, one important task is there, for example, zero or low resource speech research. Okay, so what it means actually, in some of the work, for example, when you go to pathological speech processing, so in that time, what happened? You may not have huge amount of data. Like nowadays, if you want to develop speech recognition system, in open source itself, you will get like 10,000, 20,000 hours of data easily. for English or maybe for Hindi, you will get some lower amount of data, but you will get that. But for some pathological speech, you may not get that amount of data. Okay, but if you want to do a very good system for those speakers, then you need something that problem is called low resource problem. Okay, in another case, for example, you want to do some work on some tribal language, for example, where that language presence in the digital domain is very less. Okay, so for those areas, for those applications, we call low resource speech research. Okay, so in that application, actually, we need this kind of foundation models where we can get that model and then we can do whatever task we want to do. So now these are the information actually it's encoded in that speech signal. Okay. Now how to there are different benchmarks are there for speech research. So if you want to do whatever research you want to do, you can take some initial data to do your work, because you need to build something. So you need to download this data and you can do, for example, library species for ASR. I think you might have you know all those things now if you are into speech research, for example. Then this is just a simple speech signal, and it is spectrogram representation. Okay, and then these are something like IPA representation of its phonemes. And if you see here, this speech signal, this is your message. For example, whatever that person is speaking, she tried to make herself sound younger than she was. Okay, then this is like word level segmentation. Okay, and then this is phone level segmentation. Okay, now this kind of segmentation is required for different application. Okay, for example, if you want to do in pathological speech analysis, so you want to understand like whether that person is speaking one particular phoneme correctly or not. Okay, so then this kind of segmentation on this kind of analysis is required. Okay, now this representation, whatever it is there, like this sentence level representation or then word level representation, okay, and how to get those things. So this from the speech recognition, you can get that for some information, for example. Okay, now whatever work you will do, so you need some kind of representation. Okay, so when you get the speech signal, okay, so speech signal is it contains huge amount of information. Okay, and lots of maybe redundant information also. Okay, but when you build some kind of models, maybe machine learning models, then you need to represent that speech signal to some another representation. Okay, and earlier days when this deep learning evaluation, deep learning these big models are not there, at that time when we used to do is that we extract features. Okay, so what we do actually to extract the features is that just to get some compact representation of that whole speech signal. Okay, now one famous this one widely used representation is called frequency, this one male frequencies of some coefficients. Okay, so if you read speech signal textbook and course, then you already studied these features. Okay, so it is a very compact representation. Okay, but these representations are called handcrafted representation because we use signal processing techniques to build signal processing as well as how speech is produced, and this speech production or speech perception knowledge we use to develop this kind of features. Okay, so there are different steps are there, and using that steps, when you pass the speech signal, you will get something called MFCCs. Okay, some representation. Now before speech, before this kind of deep learning era where we're not able to use that signal directly, speech signal directly. At that time, MFCCs, those are very efficient way of modeling, building that system. Then we do some windowing and all. Then this is the male filter then. Okay. Then another representation is called spectrogram representation. Okay. So when you do the this one, your MFCC extraction, first you need the representation, you need to convert to a spectrogram representation, and for each slice you are doing some kind of processing. For example, this kind of processing you will do, this kind of DFT, then passing to mail filter, and then computing the CT. Okay, like that you will do. So without doing anything, when you compute the raw spectrogram, so that representation also we can use to as a input of the machine learning system. Okay, and on top of that, if you pass this spectrogram through some kind of mail filter bank, then you will get mail spectrogram. Okay, so that representation also people use for to learn the for example, to as a input of the machine learning system. Okay, so these are some kind of representations, but these representations are handcrafted, and we use signal processing and speech production, perception, those knowledge to develop this kind of features. Okay, so MFCC is not only one of the features. LFCC is there. Then in the other different features you will get from internet, from papers and all, and even from your textbook also. Now, why we are moving to this kind of foundation models? Okay, so we need some kind of representations. Okay, now earlier whatever representations we get, as I mentioned, those are signal processing based representation, not data driven representations. Okay, so what do you mean by data driven? So depending on your task, that representation may change. Okay, if it is, for example, if it is a speaker recognition, and if it is a emotion recognition, your representation will change. Okay, but in case of MFCC, those are fixed set of vectors only. Okay, like whatever signals you are giving, and then if you compute the MFCC, those are fixed. Okay, and depending on your data, we are not modeling anything there. Okay, now what do you mean by foundation models? Okay, now foundation models, what is the motivation actually, like why people are coming with this kind of big foundation models? Now when you see when this deep learning era came, at that time what happened, if you want to build something very good performing deep learning models, those are very costly. So just assume, like if you want to build speech recognition system with some 10,000 hours of data, so it is very costly, okay, to build that model, and it involves like data collection, then data annotation. Okay, then you need like computing power, then you need training time. Okay, now if you want to repeat that system for another like 10,000 hours of data, again, like you need huge amount of computing power, then time and everything, like data annotation and all. And another problem is that if you want to build something on very low resource setup, like I want to build something on, for example, maybe in Orissa, like you have different tribals languages are there. So if you want to build system on that, so it will be like quite difficult. Okay, because you will not get transcribed annotated data. So these are the problems. Okay, now then people are thinking like, can we use the huge amount of unlabeled data available in internet? Okay, because if you see in case of speech, if you see that in YouTube there are huge amount of data is there. Okay, but those data are unlabeled in the sense for each audio you may not have the transcription. Okay, but what they are thinking is that we don't need that transcription, we need only the raw audio to build some model which may act as a like as a basic base model, and on top of that we can build our whatever task we want to do. Okay, so in that way the foundation model came, and they leverage all the unlabeled data whatever exists in that open source. They use that data and they build one big model. Okay, how they are building, just ignore it, just they build that model. Okay, so once you get that model, so that model will give you some kind of representations. Okay, for when you pass one speech signal through that particular model, that big foundation model, then for that particular speech signal you will get some representation. Okay, representation means you can assume some vectors you will get. Okay, those we will call embedding vector. Okay, so those embedding vectors will have that information, whatever you want to solve. For example, if you want to solve emotion recognition, then maybe emotion related information will be there. Okay, if you want to do something like speaker related task, then that speaker information may be there. Okay, so that model you can build, and with very small amount of data you can build your own model. Okay, so if you have very small, maybe 1 hour or 2 hours of emotion data, using that also you can build uh, your good models on your low resource setup. Okay, and to train a 1 hour data may be very easy. You can use your own CPU or own model to own competing setup to build that model, and for annotating 1 hour data is very easy. Okay, so that we can do. Now this field of that foundation model, so it is recognized that natural language processing area. Okay, so you know about BART, GPT. Okay, then this kind of models you already know. Now how to build that model, that foundation model? Okay, so one kind of learning which is called self-supervised learning. So that is a promising technique for developing foundation model. Okay, so it will this technique train a huge amount of train a big model. Big model means models with very huge number of parameters. Okay, and they use unlabeled data, and those models will learn some kind of something like representation, which are which may be useful for different applications. It may be ASR, it may be TTS, or it may be your language identification. Okay, so those representation you can use and you can do your own work. Okay, now before going to like speech this your SSL, that means self-supervised learning, let's see like let's refresh our basic machine learning. Okay, so let's this machine learning algorithms, we take sample of data, then we do that training based on our requirement. Okay, so let's consider only these two categories of machine learning. Let us ignore reinforcement learning. Only let's see, we have these two categories of machine learning. One is supervised machine learning and one is unsupervised machine learning. Okay, in supervised machine learning you have labels. That means if you want to build model like cat versus dog, then you have image with cat and dog, and for each cat image you have label with cat, for each dog image you have some label called dog. Okay, then you build some model, maybe SVM or decision tree, different or logistic regression, you can build model, or even neural network. Okay, now in case of unsupervised learning you don't have that level, so you fit some clustering algorithm and try to segregate that data. Okay, so this is unsupervised and this is supervised. In case of supervised you have labels, in case of unsupervised you don't have labels. Okay, but supervised machine learning is easy to, like, you will get good performance whatever state of the art models are there. Unlike to that, like unsupervised learning, you may not get that much of performance. So that is why, like, people are thinking like, can we get that motivation? For example, it should be supervised, but we are not going to annotate the data. Okay, so that's the motivation. Okay, how can we do that? So in case of supervised learning, you know, like regression is there, classification is there. Okay, so these kind of things you already know about that. So these are different supervised learning technique. Okay, now while doing the machine learning, what is the pipeline? Okay, like typical pipeline, what do we do? For example, this is the raw image. Okay, raw speech signal or image data, or maybe video data, or maybe text data. Okay, then you use some kind of feature extractor. Okay, so in our case, for speech it is your MFCC. Okay, so kindly stop me if you want to ask anything. Okay, so this is the feature extractor. In our case, maybe it is your MFCC. So we get some representation. which is MFCCs. Okay, then those MFCC we feed to some model. It may be MFC, SVM, it may be decision tree, it may be neural network, anything. Okay, and then you train with the labels, because you have, for each speech signal you have one label. Okay, then this kind of pair you are having, data and label. Okay, with handcrafted features. So there are another paradigm which is end-to-end. Okay, so in this case we are having feature extractor that is handcrafted. Okay, but another way what we can do, instead of some handcrafted feature extractor, what we can do, we can use some CNN layers. Okay, so we'll feed the raw speech, and that CNN layers will learn the representation, and then there will be some linear layers. For example, some perception will be there, and then it will feed to that multi-layer perception. That whole network you will train together. Okay, so these CNN layers will learn those features related to your task, and this is your end-to-end. Okay, now here the advantage is that left hand side, whatever you are seeing, the typical conventional one, you can have less amount of data to build a good system. Okay, earlier days you know about that. Okay, but in this case, one important factor is that you don't need any kind of feature extractor. Okay, because you don't know which feature extractor may be good for which task. Okay, so that's why we use MFCC for conventionally for everything. Okay, but in this case, the CNN layers will learn the feature itself based on the task. Okay, if it is emotion, that it will learn differently, something like that. But the issue is that it needs huge amount of data to learn this system. Okay, so these are the typical two things we can learn. Okay,
So,
now, yeah, yes,
sir, I have a question. Can you go back to
sir,
that last slide?
sir,
Last
yes.
slide.
Yeah.
Yes, yes, sir. So here, firstly, when you are elaborating about the foundational models or large models which are there,
Yes, yes.
by which some big unlabeled speech data is put is given to a model, and it is trained in that way, and if we have some little bit of 1 hour or 2 hour data, we can use to fine train that model and get a good result. That was when you were talking about. So
Yes,
that big model is like that second, right? The second.
No. This is not that one. Okay, because in that foundation models you don't have labels actually. Okay, but here this is supervised learning. I am just telling labels are there. Okay, these two things are same only, but here we are learning end to end. Here we are not learning end to end. That is the only difference.
So here one CNN model is there which will extract the feature, and after that it will create some intermediary product that will pass to the classifier, and it will get the labels. It is like that only, no sir?
Yeah, it is like that. But here, whatever learning we are doing, so we need this pair, correct? No, this data and label pair is required. Okay, to learn this jointly, to learn this jointly, this feature extractor and predictor. Okay, here we are not learning that jointly. Where feature extractor is different, our predictor is different, independent. Okay, but here single model. But one problem here is that you need labels, correct? You are building on top of the labels. You need data and its corresponding labels. Okay, got it? Huh?
Yes, sir. So you have talked about some embedding. So in this case, in the left hand side, we are, sir. I'm first in the left hand side, we're extracting the MFCCs. So here in the right hand side, we are not extracting the MFCCs. We are extracting those embeddings kinds of things. Is it like that?
So that's what I'm telling. So we are actually not doing. We are not extracting anything. Okay, these are internal representation. Okay, we have like these CNN layers are there. Then this some last layers will be, some linear layers will be there, and we are learning together. Okay, and with respect to some labels. Okay, this is a supervised learning. Okay, for example, you want to just take some CNN layers you are using, and then some linear layers you are using. Maybe here you can use some maybe LSTM layers also, and then you are predicting something. Okay, got it now? This is end to end you are learning. Okay.
Yes, sir. Yes, sir. Understood.
Okay.
Yeah.
But you are not learning any representation. Okay, which you are going to use. Okay. Fine now. Okay. The problem here is like you need the supervised data in this case also. Here too you need supervised data. Here also you need supervised data. Okay, to build that. Actually, this CNN layers will be there in foundation models only. But what I am telling is that in this kind of end-to-end learning, you need the data and its level pairs to jointly learn these two things like predictor and feature expected. Okay. Now there are two things actually in case of pre-training. One pre-training is we call your transfer learning based pre-training, and one is like self-supervised based pre-training. Okay, so now what is transfer learning? Okay, so here, for example, in this case, if you see, you have huge amount of data. Just I'm giving one example. Let's assume that that gigaspeed data, gigaspeed model, the data is there, right? In that gigaspeed data, or what I can say that Foxelab, you know, if you know anyone, like that is a speaker recognition data. So it has around like 7,000-8,000 of speaker. Okay, I'm giving one example in this end-to-end case. Okay, so you take that 7,000 speaker data, okay, and you build one model. Okay, now that is an end-to-end model. You are feeding, you are giving that speech, and then you are putting some CNN layers. Just take an example that TDNN model or ICAPPA TDNN. So those models are there actually for speaker recognition. So you take that model. Now in that scenario, what happened for each audio file, you have the speaker levels. So that is a level data, correct? So that level data from Voxelab we download. Okay, and then we build these end-to-end models. Okay, correct. And this is a supervised model because we have data and speech and its level, speaker level. Okay, now what happened? For example, you have some other in your place that maybe that whatever model in Voxelab is there. For example, that is trained on some like some few languages, maybe like 10-20 languages are there in that Voxelab, and that data we use to train our model. Okay, for example, I want to build one model for Assamese speaker. Okay, so what we can do, one way is that we can take that model, we can take this model, and then because this model already learned some kind of speaker representation. Okay, then what we can do, we can just fine tune this predictor. Okay, predictor using our Assamese data. So maybe some 200 300 Assamese speaker data, we can fine tune this predictor. Some these layers we can fine tune. Okay, now this is called your transfer learning. Okay, because whatever model we build, that base model, that is a supervised model, and we use that supervised model to learn our new data, which is the Assamese 100 speaker data. Okay, got it. So this is called transfer learning. Okay, now the problem with transfer learning is that whatever base model you are building, that is actually your these terminologies are actually like interchangeably people use, but the problem here is that you need huge amount of level data to get the good representation. Okay, so you can see like this transfer line uses level data to learn good representation. Okay, so this is a supervised person. Okay, so you can read this paper actually, A Tale of Two Pre-Training Paradigms. This is a good, very interesting paper. So now in case of self-supervised learning, you don't need that annotated tables. Okay. Now this transfer learning, as I mentioned here, you can use this, you can assume this case also. You have these convolution layers, right? Okay, you can freeze these layers where learning rate equal to 0, and then you can learn this layer only. Okay, so let's consider you have a trained model on ImageNet data. So ImageNet data is your level data, right? So one model is trained on ImageNet data, and in ImageNet maybe thousands of classes are there. Okay, but you want to build one model where these ImageNet classes are not there. Okay, you want to build some 10 class classifier where these ImageNet levels are not there. Okay, so that 10 class, you got some like per class, you have 10, maybe 10 examples are there, 10 images are there. So 100 examples you are having. So you can freeze these layers and then you can learn that. And then you get your level should be like here of only for 10 class. Okay. So that way also you can learn that model. So this is called transfer learning. Okay. Fine. So why actually transfer learning works? Because if you see in case of image like this earlier layers, like that beginning of that layers, no, it will learn some kind of basic features like edge, corner, all those things it will learn. Okay, and it will go upward. No, upward means this one. This is your first layer, so it will learn something like basic features, maybe edge, curve, all those things. And once you go to this deep to that model, it will learn more difficult representation. For example, this kind of seer or something like that. Okay, so even in speech also something like that happens actually. Like initial layers, it will learn some basic features. For example, your what is called that information within like few seconds maybe. Okay, when you go to that upward direction, like in that deeper layers, it will learn more your semantic or more your prosodic kind of information. Okay, so those kind of things are there. Now, what is the self-supervised learning based representation? Okay, now here see this one, we have two steps actually. Okay, so what two steps are there? In case of self-supervised learning, as we mentioned, we don't have proper levels. Proper means we don't have any levels. Okay, so what people will do is that they will generate labels from the data itself. Okay, how to generate that labels from data itself, that we'll discuss. Okay, so you have some kind of huge amount of speech data. We have some kind of these models. Okay, these are big models where we have some kind of feature extractor model, and these representations are there. Okay, and here some kind of pseudo predictors are there. Okay, where it is pseudo predictor? Because we don't have actual labels there. Okay, so we generate some pseudo labels. Okay, so using that pseudo labels, we learn that models, and then we detach this feature extractor, and then we learn some representation, right? So using that representation, we use some kind of downstream task where we have labels. So this is your step 2, which is called fine tuning. Okay, this step is called pre-training, and this step is called fine tuning. So in that case, you will not learn anything on that fine tuning stage. You will make this model fixed. Fine. Now, what is the motivation behind that this self-supervised learning? Is that like now when big data revolution came, right? We have huge amount of data like distributed in internet. If you consider for text, we have huge amount of data in Wikipedia, huge amount of data in your social media. So those data, can we use that data where levels are not there? Okay. And second thing, in earlier days, right, you have you don't have much computing power. Okay, you have computing power, but it's very costly. But nowadays, like, you will get GPU in Google Colab itself, okay, to train your model. So that is one very good thing. Other things are there, whatever that supervised representations, whatever is there. For example, you want to train one model on specific tasks, because in case of speaker recognition, if we use that voxelab data to get the representation, so that will only be useful for speaker recognition only. It will not useful for speaker, for example, speech recognition or emotion recognition. Okay, correct, no? So that's why we need some representation which is universal. It can be used for different tasks. Okay, so that's why can we leverage those huge amount of data to build something like that. Okay, and second thing is this most important, the availability of data for low resource applications. Okay, so in case of speech, what is the problems are there? So speech is very high dimensional signal. Okay, and it is variable length. Okay, if you consider the this one, your text. Okay, 1 2 3 4 5 6 7 8 9 10, only 10 words are there. Okay, but if you consider here that speech signal for that particular 10 word, it will be like huge. Okay, it may be like 5-6 seconds of data. If it is 16 kilohertz, then it is 5 into 16. So that many samples will be there. So it is too dense. Okay. And then different variabilities are there, like speaker, accent, recording condition, all those variabilities are there. And it has a complex hierarchical structure. Okay, as I discussed in that beginning, now we have a hierarchical structure. Okay, so this is your textual information. Then maybe on top of textual information, we have prosodic information, emotional information, tonal information. Okay, then you have some kind of like word level information, then your phoneme level information. Okay, different hierarchical representations are there. Okay, and in case of text, we have clear distinction, right? Okay, so this is C, this is stride. Okay, so these are clear distinctions there between each word. But here it is quite difficult. Okay, it is no clear segmentation into word or other units. Okay, it is quite difficult to segment. Okay, you can do the segmentation, but it is not easy. Okay. Now, so considering those motivation, people are thinking like, can we build something related to that? Okay. Now, I need to complete in 1:30, right? Okay, I'll give some motive, this what is self-supervised learning, then I'll directly go to the first speech. Okay. Now, in case of self-supervised learning, as you mentioned, we don't have label in the data. Okay, we take the data as it is. Whatever data is there in internet or directly raw data, raw audio data, we'll take. Okay. Now, how to get the labels then? Okay. Now you can see this term self-supervised. One thing is that it is supervised learning. Okay, it is not unsupervised learning. In some sense, actually, we can say it is unsupervised also, because we are not using any levels from our side. Okay, but it is generating the levels from the data itself. Okay, so that's why it is called the self. Okay, now why it is self-supervised? For example, let us consider this is a speech signal. Okay, then what will happen? This is time axis. So what you are going to do, you will show the model this part of the data. Okay, maybe you have a speech signal of 3 seconds. Okay, so what you can do, maybe like you can show 1 second of data to the model, and you can ask the model to produce another 2 seconds of data, and you can compare it with the original data. Okay, because you have already have the original data. For example, this is a speech signal. You mask that. Okay, so it is a 3 second audio. Then you mask some portion, this part, and this part, and you show the model this blue part, this part, this part, this part, and this part, and ask the model to reproduce this blank part. Okay, whatever you masked. Okay, then you compare with the that whatever is there already. Okay, if it is coming correctly on that. So that is your loss actually. Okay, so that way this model will learn something universal representation. Okay, so for example, I'll just show here maybe. Okay, so predict the future from the past. So you are giving this past part and asked to predict this future part. So something like that. I'll just show you maybe. Yeah, okay. So as I mentioned, there are 2 tasks actually. One is like pre-training task, where you will build a model, generate one big model. And in the second part, you have the fine-tuning task, where you use that model and do some kind of downstream task. Downstream means it may be emotion or it may be speaker recognition. The task you want to solve. Okay, so this is a like this pre-training model is like you can't do anything with that model, but you can use that model to do different tasks. Okay, to use that representation, or which is called embeddings. Now, so just let's get some example like how people are training for image. Okay, then we can go to speech. Okay, so here what you'll do is that you will show the model this one part, like this is a whole image. Okay, then you make some paths of the image. Okay, you make some paths. For example, this is one patch. This 1 2 3 4 1 2 3 4. For example, this you ignore. 1 2 3 4 5 6 7 8. Okay, these are some paths. Okay, now what we need to do, I will show the model, this first part, this patch, this one. Then I need to ask the model to predict this part. Okay. Or I will show the model this part, then I'll ask model to predict this part. Okay. Now, while asking the model to predict this part, okay, what is the advantage is that I know this part because this data already it is there in the data. I no need to label another way. Okay, just I need to like chunk it with different parts. That's all. Okay, so then maybe you can show this part and then you will ask this model to recognize. Generate this part. So this kind of things we can do. So this is one way of doing for image. Okay. The second thing, for example, what you can show is that you can show just this one relative position. Okay. Another thing what you can ask is that you just another thing also you can ask. For example, you will show this part and this 2 and 7 to your model, and you will ask which one is like which one is in top or which one is in the bottom. Okay, that also you can ask. So there you can ask different question to the model. Okay, and you can learn different way. So that is one thing. Then another thing is that in the video, for example, so this is a sequence of video. Okay, just this one. Okay, so this is the ordered sequence A, B, C, D. Okay, so video means what? It is a sequence of frames, right? So this is a order like A, B, C, D. So now what you'll do is that this is your original video. Okay, now this is your original video. Now what you will do, you will shuffle that this one. You will shuffle that images. Okay, for example, you are making this data. Okay, like B, C, A, D. Okay, then you will ask the model to predict the right sequence. Okay, so this is another way of giving the model task. Okay, so this is one way you can learn the model. Okay, so there are lots of ways you can actually learn the foundation model using self-supervised thing. Okay, and another thing what you can do, there are another way. For example, this is one original image. Okay, then you do some kind of shifting operation. Okay, you distort the image. Okay, using data augmentation. So you just shift that image or make it like reverse or something else you can do. Okay, then what you can do, you can ask the model whether these two images are similar or not. Okay, and maybe you can ask different image of dog or something, then you can ask whether these two images are same or not. So what we need to do, all the cat images should be in a one cluster. Okay, it should similar, and all cat versus dog images should be dissimilar. Okay, something like that loss can be done. So for NLP, it's easy to actually learn. What you are going to do is that, see, you will have some pairs. For example, a quick, just hold on this. For example, okay, a quick brown. Okay, in the a quick brown, that quick word is green, right? So what you will do, you will show a and brown word to model and ask to predict that quick word. Okay, something like that. So you will give the two adjacent word and then ask to predict that middle one. Okay, that is one way. The GPT, right, that OpenAI GPT, how they are learning, that is autoregressive model. It will show this whole sentence and then ask to predict that last word. Okay. Then in case of Google Bard, what they will do, they will mask some of the words. For example, a quick, brown, and this lazy, they are masking, and then ask the model to predict that one. Okay. And another way it can learn is that you have huge amount of data. So you take the one sentence and ask to predict the next sentence. So which is called the next sentence prediction. So when that model will do all those tasks, right, then model will learn some representation. In case of language, it will learn how actually that language grammars are there, how like from one sentence to another sentence, how it is transferring. Okay, so all those linguistic or you mean like semantic or all those linguistic information it will capture. Okay, for that particular language in case of NLP. Okay, in case of image, it will learn how actually image is constructed and what is the information is present. Okay, for a cat, for example, that nose will be there in the middle. Okay, ear will be there in top of the nose, for example. Then mouth will be there, for example, below the nose. So all those information it will capture by that model. Okay, then you can use that information to build a different model for different tasks. Okay, so that's the these are some kind of loss function you can use to build that model, and you just ignore that. Okay, now whatever this speech, this self-supervised based foundation models are there. So the backbone of the most of the models called transformer models. Okay, I think next class Deepak sir will show you like what is transformer and all, so that you can learn that. But what I want to tell is that backbone of that all these models, whatever you can see nowadays, this OpenAI GPT or BART or any model. So this is backbone is that this model is called transformer model. So I request like you can learn this model like nicely. Like there are different visualizations how to learn this transformer model and what its layer is doing and its components are doing. So you can learn very easily. So you should learn actually this model very nicely. Okay. Now coming to your self-supervised learning for speech. Okay. So this self-supervised learning for speech actually start around like 2015. Okay. There is one paper is there, self-supervised speech representation learning, a review. You can read this paper and it has very good explanation actually. Okay. And till 2022 it is there, but after that there are large number of some large number of models it is there, but till 2020 it is 2022 it is there. Okay, so you can see there are huge number of models are there. Okay, and in that case I'm going to discuss Web2Vec, then your Hubert or WebLM. Only these three models we are going to discuss, and you can see like other models also. Okay, so as I discussed, for there are two steps. One is speed training. Okay, and you have huge amount of data, and it will learn some kind of hidden structure of the speech signal without considering any specific downstream tasks. So when you learn in the pre-training task, it will generate some pseudo levels based on that whatever we discussed. It will mask some part and it will ask the model to generate, and then it will learn some representation, and those representation you can use for other tasks. Okay, in the downstream task, so you can use that pre-trained model and take out that representation for each audio signal and build a classifier. So this classifier may be your neural network or maybe SVM or decision tree or simple logistic regression or simple cosine similarity. Okay, so you can use to build that model. Okay, it is so powerful. It will not require a very big model to build on top of this. Okay, you can use very simple model to build that. Okay, so that is the big advantage of having this pre-trained model, and it will require very less amount of data. So these three models let us discuss. So when this Web2Vec model came, like it is a very successful model from this Meta research. So it learns very powerful speech representation from huge amount of unlabeled data. If you go here, you can see these models are there. So they use something called contrastive loss. So what it means actually, so for example, you have a speech signal. Okay, then you mask some part. Just I'll get to the next slide should be there. Okay, so what they'll do, these are some layers. Okay, these are some CNN layers. So these are typical CNN layers, like whatever we use generally. So these are CNN layers, and on top of CNN layers, the CNN will extract the features. Okay, so CNN will learn the features, and then those features will input to a few transformer layers. Okay, now these transformer layers, so if you see here, for each transformer is CNN layer here, whatever it will pass through that transformer network, then it will learn something. Okay, and then whatever you are passing right from that CNN layers, it is called the context. Okay, context vector. Okay, so for example, for this one, it will go to and it will generate the context vector. Okay, then whatever is this one, this is called Q, right? Okay, so this what is called that I think this is learn parameter or something they are calling, learn context or something. This representation you are getting. Okay, and then what they are doing is that they are quantize this representation. Okay, now and then another representation, whatever this L is there, they are generating L. Okay, you can assume this as a feature, L feature, and it will pass through this transformer network and it will generate some context vector. Okay, now this same L vector, it will pass through some quantized network also. Okay, then what that network will ask is that similar kind of context and quantized vectors should your merge to should be the similar category, and other other like representation or other like context whatever is generating from a different part of the speech should be a different thing. Okay, should push to a should push to like should push apart. Okay, so whatever that similar kind of representations are there, it should combine, and whatever that different representations are there, it should push away. Okay, so that is the contrastive loss. Okay, so to train that huge model, they actually use different different multilingual library speech, then common voice data. Okay, so they use around like Vox Populi, so around 4,000 4 lakhs something 4.5 or something lakhs hours of data to train this huge model, because this much of data training is not feasible for our. Okay, that big company can do that. Okay, who has huge amount of resources and all, and then you can use this model. So once you get that model, so this network, this context vectors, so these context vectors you can use for different purpose. Okay, recognition, translation, classification, like that.
So,
yeah,
sir, I have few questions here.
yes.
So this speech is first passed to this convolutional neural network. Then this AL is extracted, right?
Extracted, huh?
Then we are passing this AL is a representational vector, can say. So then AL is passed to this transformer, then and transformer is doing what? Generating this context vector. Context vector is what? It is trying to replicate the original signal, or
so here actually this so now what happened, this will this context vector will learn the your what is called that, I mean contextual representation. I mean contextual means like what is the representation, what to say, like for example which part of phoneme, for example here I is there. Okay, so this R representation across all. Okay, so this kind of representation it will learn from that context vector. Okay, maybe I will
and how this contrastive loss is calculated? Can you explain it again, sir?
yeah, one second, I'll do that. Yeah, so here for example, when they will learn, I mean, no, I'll not say that learn word. So it will get that L vector, okay, and it will pass to something called quantization model. Okay, not model, like quantization network. Okay, so then it will get some representation. Okay, for example, here when they will pass this, no, so it will get that Q. Okay, that quantized representation. So something Gamble or something quantization they use there. Okay, and then okay, then in some part they are masking, right? Okay, for example, this part they are masking, so this color is mask 1. Okay, this color is mask 1. Fine. Okay, now what happened here, for this part also they are that L is going, right? Okay, but it is mask. Okay, now what we need to do, and for this part also they are doing the quantization. Okay, now what we need to do, I'll show this context vector. I need to predict this mask representation. Okay, so that's the contrastive loss actually. This is called latent representation error here. Okay, so this Q is quantized. Okay, so for example, these are different this layers are there. Okay, for the different your channels are there. For example, CNN. So this one, it will go, this latent representation will go to this transformer layer and it will get some context representation. Okay, like that it will go. For this part, it is a mask part. Okay, so that means we are not showing this model. Okay, that we are asking this model to learn this. Okay, I mean to get that from that data. Okay, so how they will go get, they will get this part. Okay, and then they will try to get this from this quantization layer. Okay, quantization layer. Okay, no?
Okay. Okay, so that means that the portion which is masked, that portion is also available in various parts of the speech. So what is doing it is by other context vectors which are present. By using that, we are trying to predict the that masked part, and after that we are comparing with the original context vector. Then we are
yeah, original. Yeah, because since we are passing that, we know that original one. So actually, they are not comparing with the original one. They are comparing with this one quantized first vector only. Okay, so they are. I don't have that equation. Just 1 second. Okay, okay, here too it will be difficult. Okay, so just hold on. Okay. Okay, so this is the paper. Okay, so here you can see this. This is called Fisher encoder. That CNN layers they are calling as Fisher encoder. Okay, that contextual representation with transformer. Okay, so they are getting the contextualized representation from the transformer, and second thing, they are using some quantization module. Okay, so yeah, so they are doing masking. For example, we mask the portion of the Fisher encoder output, and or put timestamp before feeding to the context network and replace them with the trained Fisher vector shared all mask the timestamp. And so this is the actually contrastive loss. So they are computing the similarity between this context. We are okay now. This is C context with that quantized one. Okay, whatever is masked one. Okay. Here too, we already know that this masked one, and this is they are competing with across all whatever is there. Okay, they are using something called diversity loss also. Like diversity loss means like how to get the quantized because they are using some kind of what is called that your code book to generate this quantization vectors. Okay, and then which code from which code book they will take the quantization vectors. So they have some kind of diversity loss in that. So they have some kind of loss function in that also, apart from this contrastive loss. So when you get that representation, okay, without doing any fine tuning and all, if you plot that TSNE plot, right, in for different languages, if you get the you take the audio from different languages and you get the representation and do the TSNE plot, right, or 2D representation of that whole dimension, then you can see like this English, German, French, these are actually clustered to a different part. Okay, this Chinese is maybe because this English German is clustering in this part. Spanish like this is clustering. Arabic here, Chinese here, So like that you can see. Okay, so already like those representation inherently giving language difference representation. Okay, so you can directly use those representation for language identification. Like that you can do that. Okay, so even for they are showing that they showed that for if you see this representation, how they are representing different phonemes. So they tried with timid data, because in timid your phone labels are already there. So you can see here this I is having some cluster, then A is having some cluster, I is having some cluster, boy is having some cluster. This BCL means silence, it is having that cluster. So this having some cluster, actually it is not random. So it is learning that phonemes also. Okay, so in some sense they are showing that. Now what is the effect of model size? For example, this they have different models actually. So one is base model. So this base model they pre-train on LibreSpeech data, which is 1000 hours of data. And then they have another open source model. This is large one, this yellow color, if you see this, they train on 60,000 hours of data. Okay, so this is actually already available in internet, open source. So they use this model. If you see here, using this model, if they use like only 10 minutes of data to build a speech recognition, they are getting only 8.2 word error. So it is very good actually. Okay, if they will train with only 1 hour of speech data, it is 5.8. Okay, if they will train with 10 hours of data, it will 4.9. Okay, so just imagine like only 10 minutes of data, they are getting good performance. Okay, but only with 10 minutes of data, you can't build a speech recognition system. Okay, but with that representation, whatever they are learning from here, or you can just use 10 minutes of data and you can build a model. Okay, so that's the actually big advantage of that. So
Sir.
yeah,
Yes, sir.
yeah, yes.
So this is applied on that pre-trained model. I mean, the pre-trained one model we have, and after that we are fine-tuned with 10 minutes of data.
So this is fixed. Okay, so this CNN transformer is fixed. After that, whatever context representation they are getting, so that they are using, and they are building some speech recognition system. Yeah.
So this self-supervised pre-training is done by the Facebook guys, because this is meta
Facebook guys. Yeah.
fine-tuning part, and after that we are getting this.
After that, yeah.
Okay.
After that, so this table also I have taken from their paper only. So you can see like they are getting very good result on that. I'll show that result for yeah. So this you can see like in 20, I think when in 2021 or something, we participated in that IIT Madras ASS challenge. So yeah, I think we saw that. Oh yeah, so you can see here like with what we did actually, we take this pre-trained model XLSR 53. So this model was trained with 56,000 hours of data. We have not done anything on that particular model. We just take that model from Facebook, and then we fine tune on our own data. We fine tune on different languages: Indian, English, Hindi, Tamil. Okay, you can see like whatever WR we are getting, it is 4.9, 4.5, 5.8. So it is almost similar with this Kaldi based model. Okay, so it is almost similar to that particular model. Okay, you can see here. Yeah, so there are different actually different person they participated with this web to web. This is long back actually 2021. Now to like very advanced models are there. So lots of persons are actually web to web, use web to web at that time. Okay. Now this is one thing, and then there are one initiative is there called XStep Foundation. So they actually built, because now whatever models we take, this is XLSR 53. So in that very few Indian languages are there. Okay, and that is not specifically for Indian languages. So the motivation here is like, can we build that kind of big model for Indian languages? So they use some 23 Indian languages on some 10,000 hours of data they use to build this model. This maybe you can check this model, and if you want to do something on Indian language, this model is also good actually. Okay, even now AI for Bharat also built that model for Indian language. This is called Indic AI Web2Vec. So they build on something 40 languages, some 30,000 hours of data they use to build that model. So you can download this model, and you can train your own model on different tasks. Maybe speech recognition, emotion, like that you can do. Okay, language identification and all. So these are two in the context of Web2Vec, in the context of this one. So this is one paper. This person has having other papers also. This interspeech actually, they are showing how this Web2Vec and all this big pre-trained model can be used for emotion recognition. So emotion, or maybe your different other paralinguistic thing. They are showing like how to use this model. Okay. Now, second model is called Hubert model. So, in case of Web2Vec, they are just learning that representation. But now, in case of this Hubert, this model is motivated from the BERT model for text. So, in NLP, we have one model called BERT. So, they take the motivation from BERT model, and then they did something similar kind of thing for speech also. Okay, but in case of image,
Excuse me, sir, I have a small question.
Right, fine, yeah.
Yeah, I wanted to ask about word to vector. So if we want to fine tune that model, that means we have to fine tune it with label data, right?
Word to vec or wave to vec?
Wave to vec, yeah.
Wave to vec, yeah, okay.
So, like, do we have to use label data to fine tune it?
Yes. So for fine tuning this, you need label data.
Okay, like the speech and then the annotation as well.
Yes. Okay, yeah. Because during the pre-training stage, you don't need label, but that pre-training stage you can't do because we don't have generally that much of use infrastructure and all. So that's why we can just take help from that big company, whatever they are building. Okay. So we can use that model, and then we can fine tune on a very small amount of data.
Okay, thank you, sir.
Okay. So now, in case of Web2Vec, in case of this Hubert model, so one motivation is that can we build something similar to BERT? Okay. So in BERT, what they have done, they have that I showed you that mask representation and all, right? Okay. So they, for example, this one. Okay. So this Google BERT. So this, they will show like a quick, they will mask some part, and then they will do. Okay, in text actually what happened, you can have some kind of discrete representation. Okay, because already it is discrete, right? Correct. In speech it is not discrete. Okay, it is a continuous signal. Okay, so what they are doing, they are getting some discrete representation first. Okay, unlike Web2Vec, in Web2Vec they are not doing that discrete representation first and then doing that. First, they are representing the speech to some discrete representation with the help of MFCC actually. Okay, and then they are learning on top of that. Okay. And this Hubert model actually take inspiration from one paper in computer vision called Deep Cluster. So you can read this paper. So they actually, I will not go with that. They take the motivation from that paper. So first thing is that discovering the hidden units target. Okay. So because we don't have target, right? Okay. So from where we'll get the targets? So in this case, in Web2Vec, they have targets from your they have targets from the that quantization whatever they have done. Okay, so that they have taken as your target. But here what they are doing, they use something like k-means clustering to represent that this one. So for example, you get the whole data. Okay, then you compute the MFCCs.
Okay, you have the whole data, for example, 60,000 hours of data. Then you compute the MFCC for each vector. Then you cluster it. Okay. Then when you do the clustering, this clustering also depend like how many K value you will use. So for example, you are using like 128 clusters. Okay. Then you represent for each MFCC vector, you represent the cluster. Okay. It may be soft cluster only. Okay. So then you will have some kind of representation. Okay. 128 dimension representation you will get. Okay. Those are your labels. Okay. Those are your discrete representation. Okay. Now, so when you will do the masking, you need to predict that particular representation. Okay, you have the mask representation, and then you want to compare with this k-means based representation. Okay, then you do that contrastive loss and all. So like that, they are actually doing that in Hubert. Maybe you can just read this paper. Here, one good tutorial is also there. Hubert visually explained, so you can see that. Okay. So this model also people have used, and like they showed compared to Web2Vec, this Hubert model performs better. Okay, it's very good actually. Now this few days before, maybe in June 10 or June 9, actually another paper got released. This is called multilingual Hubert. Okay, so in earlier Hubert, whatever we discussed, it has some drawbacks. For example, to build a multilingual Hubert, it needs huge amount of memory space, and that k-means clustering, whatever they are doing, it is very slow. All those things are there. Now to overcome that, they build one model. This is very compact. If you see this model, it is only 95 million parameter model. Okay, but they are showing like they are getting very good performance on LID especially. Other result you can see like they are not getting this 85 and all, but they are getting 85% here. Okay, but this model you can't compare because this is a huge model. But if you take this 95 million parameter model, this model is giving good representation actually. Okay, so people are actually expecting this Hubert will be very better than earlier models actually. Okay, so that also you can explore now. These codes and all are there. Okay, so that other thing now, whatever other models are there, Hubert and Web2Vec, so they are not specifically tuned for speaker specific work. Okay, so in that loss, they are not using speaker information. Okay, so now in this one in Hubert and your Web2Vec, so that when they tested, actually they found like for speaker recognition and speaker kind of work, that representation may not be very good. Okay, so to get better speaker representation, they are using this kind of what they are doing is that if it is a similar speaker, then you make a similar score. If it is a different speaker, you push apart those representations. Okay, so that using that contrastive loss. So this is called a wave alarm paper. So you see here, it's very interesting here. So there are different tasks there, and for different tasks, which layer of the wave alarm will be better. Okay, for example, this is your Hubert base. This is your wave alarm large. Okay, let us consider this wave alarm large. So you can see here this for speaker kind of representation, speaker kind of work, this 6, 7, those layers are very beneficial, or 6, 7, or maybe 24 class layer. Okay, for your phone recognition, this 22 number layer is good. Okay, in case of Hubert, if it is a ASR, then maybe 9, 10, those layers will be good. Okay, so those kind of analysis explanation they are giving actually. So this paper is also, that's why it is very good paper. You can read this paper. Okay, because when you want to do that a specific task, for example, emotion or language identification or speaker recognition, so out of that few layers in that that particular model, so which layer will be most beneficial for that particular task, so that you should know. So for that, actually, this paper is good. Okay, to understand that. Then they are doing some, and now this year is from the CMU. they have published one paper called a large scale evaluation of speech foundation models. So this paper, I think you should go and you should read this paper if you want to work on this speech foundation model, because what they have done is that whatever speech foundation models are there, okay, you can see this from APC, this APC factor, this still invert, this that WaveLM, all those models they have taken and they evaluate for different tasks. So what task? Actually phone recognition, okay, then your QR spotting, speaker identification, emotion, intent classification. So for different tasks, how these models will work, so they have give everything in this paper. So you can, if you read this paper, you will get all the knowledge actually for different tasks. Okay, so you can see for this is a bank, whatever earlier I told, right? This filter bank based mail spectrogram based feature you can use to build a model. So compared to that, all this foundation model based actually work is giving better performance. Okay, if you see this intent classification and all, it is actually very good. Okay, 98, 90, 95% accuracy you are getting. Okay, even in emotion recognition also, if we are using that MFCC, right, you are getting only 35%, but here you are getting 60, 67, 68%. Okay, phone recognition error rate also it is drastically reducing. Okay, so these are very good actually. So I encourage you, maybe you can use these models in your work to get and you can do different work actually, like you can have different ideas and you can explore, like, because lots of the things still people have like we have don't know, like what will be there, like when you use this foundation model, how it will work for different tasks. So still people will not know. So that's why they actually wrote this paper by this big group from CMU. So they have written this book paper this year only, like I think last month or something. So you can read this paper, and whatever task you want to, you can do that. Okay. So I think maybe I can stop that. There are another problem which is called domain shift in self-supervised learning. So for example, you web-to-vec model, if you consider, so whatever data they use to build that model, that is like very good quality of data, maybe headset recording data. But if you want to build speech recognition or language identification in your telephonic speech, then this model will not give better performance. Okay, so which is called domain shift problem. Okay, your trained model is on this one, your your headset data, but you are going to fine tune on a telephone channel data. So then that data distribution is mismatch is there. So that's why that model performance is not good. Okay, so now what people are suggesting is that if you want to build model for your telephone speech, but your pre-training was done in headset data, so what you can do, that pre-trained model you can take and maybe you can run one epoch with the unlabeled telephone channel data. So that kind of suggestion people are giving actually. Okay, so these are the things actually. If you have any question, you can ask me now. So I'm like almost complete. It is done from my side.
Sir, I have a question.
Okay, yeah.
So my question is, these models, these are pretend on very large data set. I mean, almost 10,000 hours of data. This Web2Vex.
10,000. I think now whatever models you will see, like those are like 3 lakhs, 4 lakhs hours of data actually. Very huge. Yeah.
So I'm asking that, yeah, if I fine tune it by some cross-lingual speech, will it give for ASR? Suppose I'm right now in India, most of us speak while speaking in a language, we mix up some different languages. Like while we're speaking in suppose in Bengali, we mix some English words or some Hindi words. So in that kind of speech, we used to fine tune the model. Will it give a better performance, or we have to use a separate model to separately identify the language first, then put it for the
No,
transcript?
not required. No, not required. You can use directly, like if you have that level data, directly you can use that. So that is called code switching, whatever you are telling, right?
Yes, yes, code
You are
switching.
mixing with English or different language. So you can directly use, so it will work perfectly fine. Yeah. But what you need to do on top of the model, you should have one language model. So that language model should have the text, whatever you want to build. Okay.
Yes, sir. And from language model, I want to ask another question. While in the contemporary measures, while we're building a ASR, we need a acoustic model and a language model. Uh, and I guess a phonetic model is also required. So these three kinds, these three kind of models are there, and they are put together to build the first relation between the phonemes to words and words to sentences. So while building in ASR in web to web, so do we need this kind of language model stuffs or simple while I'm asking for while fine tuning, or we just have to give the or we just have to give the transcribed speech and the does the phonetic features or lexicons are needed while fine tuning? That's my
Actually, like whatever you told, so that is called your the hybrid model. So in that acoustic model, your lexicon and then language model you need, and that hybrid model, that Kaldi based system, whatever we have been using now. So
Yes.
there you need everything. Okay, but in case of this end-to-end, this web-to-web based model or Hubert based, this foundation model based thing, that language that it will run the your language thing also. Okay, like how that sentence will form or something like that. So in some sense, you don't need the language model. Okay, without language model also you will get good performance. But the thing is that if you need good performance, so you should have a language model, because if you see these papers, okay, see here, you can see right here. So if it is just see this large model only, if they are not using language model, so they are getting like 38% WER. But if they are using 4-gram or transformer based language model, they are using like very reduced in that WER. Okay, so that is the advantage. But still, like you can see here, if your data is increasing, then your language model requirement is also like not required maybe. For example, if you have 100 hours of level data with this big model, 60,000 hours of pre-trained model, then without language model also you are getting what 3.3% WER. So that is very good. Okay. But the thing is that in domain specific work, right? Like if you want to build something on travel, okay, so it's always better to have a language model in especially in case of production environment or like whatever work we are doing in company, right? So we need a language model. Otherwise, what happen? It will give more good performance. So that is the factor.
Thank you, sir.
Okay, so if you have any other question, you can ask.
Yes, Bala, do you have any questions? Bala or Isa?
Yeah, excuse me, sir. I would like to know which one is better, that Wave 2 to Vec 2 or the other one, the second one, Harp or something.
Oh, Hubert. Okay, so here actually, like, so these three models, if you see, this web to web, if you see read this Hubert paper, so they are showing this compared to web to web, Hubert is better in terms of ASR and all. Okay, but in case of if you want to do something on speaker recognition related task, then WebLM is better. Okay, because they have that loss function. And now, as I mentioned, this AM Hubert came few days before, so that is better than that original Hubert model. So that you can explore. This model is better, and they are showing it is the best one compared to Web2Vec and any other model for the language identification. you can see that compared to WebLM also, it is better. Here you can see this. So if your task is language model, not language model, I mean language identification, then this Hubert is better actually. So that's the thing. Yeah. Any other question you have?
Okay, thank you, sir.
Thank you.
Could you please share us the PPT so that we can also
Sure,
refer?
sure. I'll share it with sir. Maybe you can. Okay.
Okay.
So before completing my work, I'll just give you one. We have one. We started one initiative we call Assam initiative. We started maybe 2 years before. So we are continuously we are having different lecture series and talks, and some internal events also. And we are planning for very good sessions and all. Maybe you can visit sometimes. Like I'll let you know. Okay, I'll let know certain answer, because in the next month we are having 2 good talk on voice privacy and some speech recognition from different scientists, one from UK and one from Netherlands. So I'll let you know if you want to attend. So we had different series on LLMs also. So you can visit our this one YouTube. So this is a non-profit initiative. So we are planning to like build community, and then we are planning to give AI education to this part of India especially, but it is open for all actually, because our medium of communication is English. So yeah, you can attend and you can maybe share with your friends for this one. Thank you.
Sure, sir.
Okay, thank you. So maybe you can wrap up that.
And does anyone have other questions they can ask? Yeah, and for the attendance, sir has not given me the attendance link, and sir is not here, I guess. So I'll tell the sir to take the attendance from the last session and try to join the next session as well.
Okay. So
I'm
so,
telling. So
okay,
sir, please continue.
Okay, so I'll leave this session. Thank you once again for giving me this opportunity. Yeah.
Thank you very much, and it was really a wonderful session, and we have learned so many new things. Yeah, thank you very much.
Thank you. Thank you. Thank you. Thank you.
Okay, then everyone should drop off that session, because I can't end the session. So everyone should just drop off from here, and we'll meet again at 3 o'clock.